So first of all, I will tell about what is strongly correlated materials at all, and two methods which were invented to treat them: LDA plus U, LDA plus DMFT, and some typical results. First of all, why we are interested in these correlations at all? That started after the discovering of cuprate superconductivity. Before that, nobody was interested in it because that's usually a transition metal oxides and nobody cares what they do. Now, after cuprate, they have found a lot of other interesting materials belonging to this group, so now everybody is interested in it. Yeah, that's it. So that's methods and some applications. Then DMFT method in its applications. Now, what are those correlations? That's a very beautiful picture, done by not me, but I like it very much. So that is density functional of one electron theory, when all electrons in the crystals move in the same potential independently, non-correlated. Their passes are not correlated with each other. Then, if they live long enough on one of the atoms, electron, then when a second electron came there, they will feel repulsion. Then they will avoid each other, those electrons, and that means they will move correlated. Their movement will be correlated, hence that's the name. Now the scheme where we need correlations, where not. So the major parameter is the ratio of Coulomb interaction parameter U, Coulomb repulsion energy for two electrons on the side, to the bandwidth W. Bandwidth is proportional to hopping parameter from one atom to another, and it is inversely proportional to lifetime of electron on the side. So if you have broad band, lifetime is very small, and all electrons feel average potential. If bandwidth is small, then lifetime on the side is large, and then electrons have a time to feel each other. So that is a ratio. If this ratio is small, so these correlation effects are weak, then standard LDA or density function works pretty well. So we have quasi-particle bands and nothing else. Now, opposite limit, when UW is very large, that is for atoms, for free atoms, ions, or for example, f-electrons of rare earth. Then they are completely localized, and they could be described by free ion picture. The most interesting case is when we are in the middle, when UW around 1 ratio. Then simultaneously we have localized features in the spectra, so-called Hubbard bands, lower and upper Hubbard band. But at the same time, we have bands, quasi-particle bands. And that's not different electrons. The same electrons gave us localized and itinerant picture. That is why it is so difficult to treat. Now, how to solve this problem? Correlation effects were treated in model Hamiltonian, Hubbard-Anderson Hamiltonian, but then it's model. You need parameters. LDA density function have everything, and they have hoppings, bandwidths. Even we could calculate Coulomb direction parameter in LDA. So the idea is to combine both approaches, model Hamiltonian and density function, into these two methods, LDA plus U, LDA plus DMFT. Difference between is the following. LDA plus U is static mean-field approximation to model. DMFT, just by its name, Dynamical Mean-Field Theory. The field is dynamic. It is energy or time dependent. Now, that is how this approach works. In LDA, we calculate one particle Hamiltonian for itinerant state. for localized states as if they will be bands, then hybridization between two sets, and then concentration parameters. Okay. So now the key part, that is Hamiltonian. So we have so-called non-interacting Hamiltonian and Coulomb interaction. Coulomb interaction is simple. That is product of occupancies. ILM, that is orbital indices. I site, L and M orbital and this projection. So idea is the following, that if you have both occupied, both n are 1, then you have energy repulsion. If one of them is 0, you have not. So that's Hamiltonian, and the so-called double correction problem, because in density function we have already Coulomb interaction, but in average form. So we should subtract average term and add full-scale interaction. Now, that is the simplest form of LDA+U, static mean-field approximation, where operators, occupancy operators, are replaced by average number, occupancies. Average value of occupancy operator is occupancy, it's a number. And that is why it's called static mean-field, because we use just a number, average number, independent on energy, time, and so on. So then, that is the effect. Now, energy of the orbital depends on the occupancy. While in density functional, all electrons have the same energy, the same potential, dependently on occupancy, occupied and occupied. But now, occupied states will be shifted down. Unoccupied state will be shifted up. And that gives us Mott-Hubbard gap equal by U between occupied and occupied states, or between lower and upper Hubbard band. That is the key point. Now, with this correction, we could reproduce Mott insulators. While, for example, if you have very narrow band for metals, rare metals, in LDA, they always will be partially filled narrow band on the Fermi. Now, with this correction, we immediately will have insulator. That is a general form. When we have a matrix, that's important, because here we have an occupancy matrix, so that we could use basis invariant formulation. Sometimes we do not know proper basis. Now that is how it works. If we have occupancy matrix, then potential is also matrix. Matrix in orbital indices. Now, that's a very interesting trick. If we know all eigenvalues and eigenfunctions, yeah, then we could immediately calculate Heisenberg exchange parameters. I mean, parameters that define the coupling of magnetic moments on neighboring sites. From this, we could immediately know not only if this material is ferromagnetic or antiferromagnetic. We could calculate Curie-Néel temperature. We could calculate ordering temperature. We could calculate neutron diffraction. And that is directly from LDA+U eigenvalues and eigenfunctions. Now examples, applications. Here we have gadolinium. That's exactly what I said, that if we would calculate gadolinium with 7 electrons in the F band, that could contain 14 electrons. It will be half-filled F band. Then we will have it immediately on the Fermi. So this very narrow band would be immediately on the Fermi and partially filled, which is completely wrong. For rare metals, there is nothing on the Fermi except SPD. F-electrons are not on the Fermi at all. Now, the simplest approximation, which moves down occupied and up unoccupied states, gave us very good agreement for spectra, photoelectron spectra and inverse photoemission spectra. So it not only split them, it moves bands on the correct position, which is important. So that is for completely localized F states. And now something much more important. Transition metal oxides. As you see, now there is no narrow, sharp bands. Bands are relatively broad. Even D bands, you see, they are relatively broad. Nevertheless, ratio of UW, Coulomb parameter, and band width is large enough to produce insulator. So this particular material is called parent cuprate, or parent high TC superconductor. Parent means that it is undoped antiferromagnetic insulator, while after doping it will become a metal and superconducting metal. So this is parent, which means that it's experimentally antiferromagnetic insulator, but standard density functional will give you non-magnetic metal, while LDA+ U immediately give correct ground state. Here, you see that only unoccupied and occupied D states are shifted up in energy unoccupied, below occupied, and that stabilizes insulator. So LDA+ U correction stabilizes insulating solution, and the antiferromagnetic as well. Now, but if it would be only produce a gap after we introduce splitting of state, it would be obvious and not so interesting. Now I will demonstrate how these methods allows us to reproduce correctly physical properties, important physical properties. It will be charge ordering, orbital ordering, spin ordering, and metal transitions. So first, it will be charge order in magnetite. So in magnetite, we have 3 valent ions, tetrahedral. They are dead, which means they are not interesting. But also we have in tetrahedral position either non-integer valency, 2.5, or below Vervet transition, we have 2 types of sites, octahedral position, which are interpreted as 2-valent and 3-valent. And here it is shown how structure looks like, pretty complicated structure. And here you see shown only iron in octahedral position, nothing else. Now that is the result. That's, as soon as we applied correction, immediately we got beautiful charge and orbital order. I should say explicitly here that formally it is orbital order. And that means that the difference in D occupancy should be 1. It is not 1. It is something like 0.1, 10 times smaller. So the general occupancy of the states is not so strongly ordered. The difference between the T to G shell, which is partially filled, is already larger. It is already 0.3. It is still far from 1. So LDA+ U method allowed us to reproduce experimentally observed charge and orbital order in this material. Now for spin ordering. When you have ferromagnetic, antiferromagnetic, it's pretty simple. In this particular case, there's a family of calcium vanadates. It's very interesting. Only one of these materials has long-range order. All others are so-called some kind of spin liquids, you could say. Or more precisely, spin gap systems. Spin gap systems mean that they do not have ordering, spin ordering till the lowest temperatures, but they have very peculiar sensibility dependence. At lower temperatures, they practically does not have magnetic response at all. And high temperatures, they typically Curie-Weiss paramagnet, and between there's something very strange. So the idea was the following. We run LDA+U calculations, obtain eigenvalues, eigenfunctions. Then from them, we obtain Heisenberg exchange parameters or exchange parameters for magnetic moments on vanadium sites. And then we have Heisenberg model, and we can solve Heisenberg model by quantum Monte Carlo. Actually, it is not solution because we do not write solution, but we could measure theoretically, stochastically, response function, sensibility, and compare it with the experimental. So that is the story. For 3 materials, we got 4 or even 5 exchange parameters. I would like to emphasize that what experimental people do usually, if they have 1 or maximum 2 parameters, they just make a fit. Make a fit to experimental data to obtain exchange parameters. If you have 4 or 5 of them, it is impossible. You could fit with infinite number of possible combinations. So, but we got immediately full set, just directly calculated. And that is the trick where we have experimental curve and calculated theoretical curve. Here, this upturn is due to the impurity, so this one when impurities are excluded. So you see it's a beautiful agreement, but a beautiful agreement for the case when we have one very strong dimer interaction. When we have frustration, that's typical case of frustration. We cannot lower temperature in quantum Monte Carlo calculation for Heisenberg model. So that's purely technical problem. So nevertheless, our first principle calculated exchange parameter reproduced experimentally measured sensibility rather well. So that was charge ordering, spin ordering. Now will be orbital order. Potassium copper fluorine 3, that is Jahn-Teller distorted perovskite. Jahn-Teller distortion is pretty interesting. It is alternatively distorted in A and B direction in plane. So that is orbital order for hole. We have D8, D9 configuration, which means one hole in the shell. That is orbital order, which was derived from experimental data. And that is the result of our LDA+ calculation for the same property. We have just draw space distribution of hole. Important is the following. We have chosen non-distorted structure. Because if it will be distorted, then orbital order is just enforced. No, it is undistorted structure. And orbital order has appeared from electronic degrees of freedom only. And then lattice will react parasitically and distort. So normally people say that Jahn-Teller distortion is the following. Lattice distorts, electrons energy lowers up. Here we say the opposite way. Electronic degrees of freedom produce orbital ordering and lattice follow that. And that is the most important part, showing why correlations are needed not only for spectra, for gaps and so on, for crystal structure. So this conference is about crystal structures. That figure shows that there are cases where you need correlations to get qualitatively right crystal structure. Here is pure LDA. There is no correlations at all. And that means that undistorted structure is stable in respect to distortion. Now, as soon as we included correlation, we got stable distorted structure. I would like to emphasize that that's not always so. There are many cases where you need corrections for electronic states, but not for lattice. But there are cases, and not very rare, when you need correlations to properly describe distortions at all. Now orbital and charge order simultaneously in manganites. So first we have x equals 0, which means that stoichiometric, where we have 3 plus manganese, and then we have only orbital order. That is the results of calculations. Yeah. Now it is 50% doped when formally we will have 3-valent and 4-valent manganese, but experimentally you see this one. And that's indeed interesting, that the charge difference is so small between two types of manganese that you cannot call it charge ordering at all. You see that size of those orbitals is approximately the same, which means that integral is approximately the same. So this charge order is more like an orbital order. Nevertheless, we could interpret it as a charge order, because all interpretation, all properties will work pretty well, describe pretty well, if you suppose that you have charge order. But you should know that just by numbers it is not charge order at all. Now, cobaltate. In cobaltate, we have pretty funny story that for low temperatures, it's a non-magnetic semiconductor. For higher temperatures, it's very slow crossover to bad metal and Curie-Weiss magnet with local moments. It is explained by the following, that you have D6 configuration, and in the ground state, you have completely filled T2G band or levels, and completely empty EG. And then you have low spin, non-magnetic phase. But very close in energy, there are excited states where you have holes in T2G and 1 or 2 electrons in EG band. And this configuration is already magnetic, but they are very close in energy. Now, we imitated temperature purely by lattice structure parameters. So you see, here you have temperature, but below it just lattice parameter. And this small change of the lattice parameter, extension of lattice parameter, when your lattice expands, your distance between atoms increases, hoppings also decreases, crystal field splitting decreases. So T2G splitting decreases, and then magnetic states become more favorable. And here, that is how we reproduce it. First, low spin states is below magnetic, but for approximately at room temperature, magnetic solution becomes a little higher. So that's how we were able to reproduce transition from magnetic to non-magnetic state. Here is a pretty funny story, which I always like to show, because it gives us the idea how strange Wannier functions can be. There's 1/8 doping, cuprate of 1/8 doping, and it is ordered material called stripe doping, stripe ordering of dope holes. First of all, the holes is spread over the whole broad stripe. the hole does not sit on one atom. It is distributed over the whole broad stripe. And we could calculate Wannier function corresponding to this hole. That's it. That's Wannier function for the doped hole. So you see, it's not only that it's very extended, it's also centered at oxygen. So it has a large contribution on oxygen, 2 neighboring copper, 4 neighboring oxygen, so a pretty extended story. So that's how Wannier function can look like for some strange cases. So that's other results of LDA plus U, iron silicide, then molecular magnets, ladders, and so on. So just to show how pretty strange and interesting materials could be described. Now, DMFT, Dynamical Mean-Field Theory. So first of all, what we have here, LDA plus U, as I said, static mean field. So potential is in projection apparatus, but the matrix element is constant, this V. In DMFT, Dynamical Mean-Field Theory, we will have self-energy operator, which could be interpreted as, again, this projection operator, but now its matrix elements depends on energy or imaginary time. So we call dynamic mean field. Dynamic means that it depends on time, but directly here it is imaginary time or energy. It's not real time. When do you need the first or second one? First of all, DMFT is much, much more expensive. Yeah? So you should use it only if nothing else works. So if you have insulators with orders, ordered insulator, sure, that's LDA plus U. When you need DMFT, paramagnetic insulators, already you need it. Para-orbital also need it. It means that paramagnetic is not ordered magnetically. Para-orbital, not ordered orbitally. And strongly correlated metals. That is the most interesting case. For example, cuprates, undoped cuprates, parent compound, just insulators, nothing interesting. But doped cuprates are strongly correlated metals, and they are superconducting. And now it is known a lot of strongly correlated metals, and they are all very interesting from potential applications. Now, what is the idea of Dynamical Mean-Field Theory? So we have atoms, and on every atom we have a set of levels, atomic levels. Now, the idea is the following. We consider one atom, but it is sitting not in crystal of interactive materials, but in the crystal of atoms with imaginary energy-dependent potential. See? And this potential is self-consistently calculated in the following way. First of all, we start with some approximation for this self-energy. Yeah? We got green function, lattice green function. Then we say, we identify this lattice green function with impurity green function. Yeah? And this impurity green function could be defined as an ion in bath. And the bath green function is defined by this Dyson equation. So we know lattice green function. We subtract on-site sigma. So now we have non-correlated site in effective medium. Then we solve this impurity problem. We got a new approximation for green function, interactive green function, and then we invert Dyson equation, and now we calculate new sigma. So you see that is important trick. First we know interacting green function and sigma. Then we calculate bus. Second, we know new approximation for G and old approximation for bus. Now we got new approximation for sigma. And then we go back and run cell consistently till this self-energy will stop changing. So we have self-consistent mean field, but dynamic. So that means that we have much simpler than before problem to solve impurity, interacting impurity, correlated impurity, not crystal, not lattice. It's much simpler, but still it's pretty expensive story. Now, how it looks like. Before, when we have static in field, we had quasi-particles with infinite lifetime. So then spectral function would be a set of delta functions. Now we have, first of all, those quasi-particles, we have final lifetime, which means final width. But also, we will have Hubbard bands. So spectral function now for quasi-particle consists of two parts: finite lifetime quasi-particle and Hubbard bands. That is how it looks like evolution for model. For Hubbard model. First, weakly correlated when U is very small, and then we have just quasi-particle bands. For very large U, we have Hubbard bands, but the most irritating part is in the middle. Mott insulator transition happens with spectral wave transfer from quasi-particle band to Hubbard bands. Not just jump, that you have 100% your weight in band and then 100% your weight in the Hubbard bands. No, it's continuously transferred. And that case is strongly correlated metal when you have simultaneous quasi-particle states and Hubbard bands. That's what is called strongly correlated metal. I would like again emphasize it's the same electrons, the same orbitals, which show you itinerant and localized behavior. And nowadays that's experimentally. That is a typical case of correlated spectra. You have something on the Fermi, that is quasi-particle band, and Hubbard bands. This line is LDA calculations. LDA can give you only Hubbard bands. It cannot give you, no Hubbard band, quasi-particle band. It cannot give you Hubbard bands at all. LDA+U could give you Hubbard bands, but not at the same time quasi-particle. So LDA gives us quasi-particle bands, LDA+U Hubbard bands. Only DMFT can give both. And experimentally, what we observe is both quasi-particle peak and Hubbard bands. Yeah. Okay, so that is strontium vanadate. Unfortunately, that's pretty bad. But you could see that partially filled T2G band. Yeah. Oh my God. What happens? Okay, so you could see something here. That is the result of DMFT calculation. We have quasi-particle band and lower Hubbard band and upper Hubbard band. And here is comparing of experimental spectra and theoretical one. That is the most important. We have correct position and the strength of quasi-particle peak and Hubbard peak. Now how it could be described. It's not only spectral wave transfer, it's also narrowing of the band. With spectral wave transfer, quasi-particle band become more narrow. That's red line LDA bands, no, black line LDA bands and red line are DMFT bands. And that could be described by effective electron mass. So we have spectral wave transfer from quasi-particle band, we have narrowing of those bands, and we have increase of effective mass. No, it works. Yeah. That is the story about V2O3, which demonstrate transition, or it just, oh my God. So what? Just wait till it reacts? Okay, let us do it this way. That's charge transfer insulator. Alexei told about this, so I will make it short. That is the most important story when you have upper Hubbard band, lower Hubbard band, and oxygen band in the between. Then you have very strong hybridization between those two substates, and that is essentially many electron effect. It cannot be described on one electron side. And now we could have well reproduced itinerant and localized states. Itinerant bands are predominantly oxygen or dispersed bands, and these flat bands are nickel. So that's comparison DMFT bands and RPS spectrum. For manganese oxide, Alexei already told, so I just say what is the trick, that here, again, there is competition between magnetic energy and crystal field splitting. Crystal field splitting favors non-magnetic state, or low spin state, low spin state, while magnetic energy favors high spin state. And with pressure, decreases distance between atoms, hopping increases, and increases crystal field splitting. So while for ambient pressure, we have high spin insulator, for low pressure ambient, for high pressure, we will have non-magnetic metal. And that's what experimentally observed and what was successfully reproduced in DMFT calculations. Here is this novel iron pnictide superconductor. And that's how we try to understand, is it correlated or not? The problem is that we have very strong hybridization between D states and P states of arsenicum. So you cannot see here Hubbard band, because if it would be, it would happen just in the place of the arsenicum. You cannot. Normally, you say correlated this material or not by looking if they have a satellite in the spectra, which is indication of Hubbard band. But in this case, this Hubbard band would be on the arsenicum, and we never see it. So our conclusion is that it's moderately correlated. We have not practically Hubbard band. This is just admixture to arsenicum band. But we have typical narrowing of the bands. So the bands of the family are narrowed, and significantly. Effective mass enhancement is 2, 3. But no Hubbard bands. And important stories, it's very far from metal transition, very far from Mott transition. So while usually you have strongly correlated materials on the edge of metal transition, here it is not. It's very far from Mott transition, but it is strongly correlated, moderately correlated. So that is, again, comparison of the RPS with calculated DMFT bands. And the last one is cerium. Cerium has very interesting isostructural transition. Below, it is for low temperatures, it's alpha phase, low volume, and it is usually considered as having delocalized itinerative states. Then, around room temperature, you have gamma phase, which is the same FCC, but with a larger volume. And then, experimentally, see well-defined local moments. So usually, people say transition between delocalized and localized F states. So what we see in our calculations, in alpha phase, we still have very strong Hubbard band, but also we have very sizable quasi-particle band. But while for gamma phase, we have practically nothing on the Fermi, very weak quasi-particle peak. So conclusion is the following, that both are correlated. Just spectral weight transfer is such that for alpha phase, we have strong quasi-particle band, which lead to the strong Kondo temperature, and all magnetic moments are screened. You don't see them. While in gamma phase, quasi-particle band is weak, and you have practically unscreened local moments. So you cannot say that in alpha phase it's completely delocalized. No, we have very strong Hubbard bands. But for experimentally, you don't see local moments. Well, then, what else was V2O3? Very interesting heavy fermion without f-electrons, then bandwidth control materials, and plutonium. We indeed tried to maybe not completely describe alpha-gamma precision, but nevertheless, we were able to reproduce strong change of localization of F states. Now, conclusion. So, first of all, we can define LDA plus correlations Hamiltonian by adding model Hamiltonian Coulomb interaction term to LDA Hamiltonian and with subtraction double counting correction. Then static mean field gives us LDA plus U, which is efficient for Mott insulators with ordering. And much more complicated, much more powerful dynamical mean-field theory can solve the problem for ferronickel insulator and strongly correlated metals. And also, metal-thread transition. That is important. The only method which could treat transition between metal threads, that's only DMFT. That's all.